Okay, good evening, guys. Okay, here is the question. Okay, for question 6.61, the vapor leaving the top of a distillation column goes to a condenser in which either total or partial condensation takes place. If a total condenser is used, a portion of the condenser is returned to the top of the column as reflux, and the remaining liquid is taken off as the overhead product or distillate. Okay, if a partial condenser is used, the liquid condenser is returned as reflux, and the uncondensed vapor is taken off as the overhead product. The overhead product from an N-butane and N-pentane distillation column is 96 more percent butane, and the temperature of the cooling fluid limits the condenser temperature to 40 degrees Celsius or higher. Okay, here's the question. For part A, using Rayleigh law, estimate the minimum pressure at which the condenser can operate as a partial condenser, at which it can produce a liquid of reflux, and the minimum pressure at which it can operate as a total condenser. In terms of dew point and bubble point, what do each of these pressures represent for the given temperature? So for part A, do you have any question or what do you don't understand here for part A?
I don't know how to calculate the partial condenser pressure.
Partial pressure. Oh, okay.
The minimum pressure.
Okay. The minimum pressure at which the condenser can operate as a partial condenser means that it wants the pressure that wait yeah, the pressure at the uh, uh, for this one it means that for the partial condenser, when a liquid is heated, when the gas is cooled slowly at constant pressure, and the pressure at which the first liquid droplet forms is the dew point pressure. You have to understand the term about the dew point first. Let you all know first. The dew point means that the pressure at which the first liquid droplet forms at is forms when the gas is cooled slowly at constant pressure. So that's why for the partial condenser, it mentions that it can produce liquid for reflux, and for the overhead product, only the uncondensed vapor is taken off as the overhead product, as mentioned here. If a partial condenser is used, the liquid condenser is returned as reflux, and the uncondensed vapor is taken off as the overhead product. So this is the definition for the dew point pressure. So understand?
Yes, I understand already.
Okay. Yeah. Same goes to also the bubble point. The bubble point pressure means that when the liquid is heated slowly at constant temperature, the pressure at which the first vapor bubble forms is the bubble point pressure. As mentioned here, if a total condenser is used, the portion of the condenser is returned to the top of the column as reflux, and the remaining liquid is taken off as the overhead product, or known as distillate. Means that both reflux and the overhead product they just produce the liquid only, uh, because all the liquid is heated at constant temperature. So So the first vapor bubble forms at the temperature of the 40 degrees Celsius here. Yeah. So that's the definition of the bubble point pressure. Bubble point pressure. So I will show my solution here. Okay. In part A, I will draw a block how to say a simple block flow diagram here. Uh, the box is referred to the condenser here. So the vapor feed to the condenser here represented by the molar flow rate of the mixture, and then S naught refers to the molar composition of the butane in the mixture, and then for the output strings, there are two output strings which consist of overhead product and the reflux one. So for the overhead product one, uh, N1, which means that the molar flow rate for the overhead product, and as mentioned in the question here, the overhead product from N-butane and pentane distillation coolant is 96 mole percent butane. So I put 0.96 mole butane per mole at here at the overhead product. And for the reflux one, uh, I put N2, which is the molar flow rate of the reflux. Okay, and then S2, which is the mole butane per mole, which is the molar composition of the butane in the uh, in the mixture. Okay, so in order to calculate the minimum the minimum pressure at which the condenser can operate as a partial condenser, it means that it want it is needed to find the dew point pressure. So you just so here's the formula for the uh, dew point pressure, which is also referred to as the minimum pressure for the partial condenser one. Okay, so for the formula one, minimum pressure equals to 1 over total of uh, the, the sum of the mol the molar composition of the gas divided by the vapor pressure of their pure species, the pure species one represented by the asterisk one for the butane and for the pentane also, because the mixture only consists of the N pentane and N butane one. N butane and N pentane one. It's the overhead product. So I just mentioned here. The, you can find this formula in the lecture notes also. Okay, and then in order to calculate the minimum pressure, this one, you have to refer to the table B.4 and Toyn equation constants. So uh, you you refer to the table B.4 to find the value of A, B, and C of the compound. This compound is mentioned here, and then you calculate it, and then you find the vapor pressure of the pure species first, of this compound first, so that you can find the minimum pressure next. So you just find the vapor pressure of the pure butane and the pure pentane. So here's the formula one. Uh, as mentioned in the table B.4, there is a formula uh, at, at that page. I see I show it to you first. Where is wait, Here is the formula one. This one, log 10p the vapor pressure of the pure species one equals to A minus B over T plus C. Okay, the P1 is represented in the unit as follow millimeters mercury, and then the T1 is the temperature in degrees Celsius. Okay, and then A, B, C you can refer to the table one for the compound, so that you can calculate the vapor pressure of the pure species one at a certain temperature. So refers back to the equation to the question uh, for the pure vapor pressure of pure butane first. You just include the values of A, B, and C. Include the formula just now, so that you will get the vapor pressure of this butane, pure butane. Yeah, and same way goes to the to find the vapor pressure of the pure pentane. And then next is you after you calculate the vapor pressure of the pure species one, and then you substitute it into the formula for the minimum pressure to find the minimum pressure. Here's the answer one. So for the minimum pressure at which the condenser can operate as a pressure condenser is this value 2595.64 milliliters mercury. Is that clear?
Yes.
Yes.
Oh,
Yes.
okay. So we proceed with the next one, which is the bubble point pressure. So yes. Okay, so for the bubble point pressure one, uh, you use the formula like this one. I think this book has the formula for the bubble point pressure one. Yeah. And this one, the bubble point pressure one. Yeah, this one. You use this one. Uh, yeah, this one. The bubble point pressure is represented by this one, the PBP one. Okay, so so the minimum pressure is the same also the sum of uh the molar composition of each species times their vapor pressure of their pure species at 40 degrees Celsius. And then uh, you already have the vapor pressure of the pure species right at the 4 degrees Celsius. And so you substitute it into the formula one, this one, and then and then and then you calculate it. You will get the value of the minimum pressure one. So the minimum pressure at which it can operate as a total condenser is 2752.16 milliliters mercury. So you guys can understand? Yeah.
Yes.
I have a question. Where you get the equation one, which yang one per
You mean the bubble point one?
no the atas
This one?
yes, the minimum pressure.
Oh,
I can't find the formula.
it is actually here. This one,
Oh,
the dew point pressure one.
dew point pressure. Oh, okay.
Yeah. This one. So can we proceed to the next part B?
Yes.
I have a
Yes.
question.
Okay.
Oh, okay. So for the partial condenser, right? The
Yes.
overhead product is vapor, and if I'm not mistaken, if it is as a total condenser, the overhead product is the liquid. So the formula you use to find the bubble point minimum pressure, which is can I see back? Can you show the bubble point minimum pressure formula? The general
This one.
formula.
This one. Oh, general formula. Wait, I show it to
Yeah,
you.
yeah.
Each actually refers to this one actually.
Oh,
Yeah.
so if yi, so the one you use is P minimum equal xi and P asterisk I, which is, so x is the mole fraction of the liquid phase, right? So
Yes.
the yi no need to use, is it? So it's just like
Eh?
the bubble point just go up
This
like
one.
that.
I mistaken.
Oh, I use that one. Okay. Oh, sorry.
Yeah. So for the bubble point minimum pressure one, I apply this one. This one. The sum of the mole fraction of the species in liquid phase times their pure vapor pressure of their pure species one at the 40 degrees Celsius one.
Also, that one is total pressure, right?
Yes.
Yes. Oh, okay.
Okay. So any question for part A?
I think we can proceed.
Okay, so I proceed. Let me see. Okay, for the part B1. Okay, now is suppose the condenser operates as a total condenser at 40 degrees Celsius. The production rate of overhead product is 75 kilomole per hour, and the mole ratio of the reflux to overhead product is 1.5 to 1. Okay, and then ask you to calculate the molar flow rates and compositions of the reflux stream and the vapor feed to the condenser. So what do you guys don't understand here? How to do it?
Yes,
I don't know.
how to do it.
I don't know which equation to use for this question.
Same.
Okay. First you have to understand that now the condenser operates as a total condenser at 40 degrees Celsius, which means that the the reflux and the overhead product just consists of the liquid one. Yeah, so let me show you the solution here. Okay, you are given the molar flow rate of the overhead product here. Overhead product here is 75 kilomole per hour, and then you are given the mole ratio of reflux to overhead product. which means that from this mole ratio of reflux to overhead product one, you can find the molar flow rate of the reflux one here, reflux one. So N1 refers to the molar flow rate of the overhead product one here, overhead product one, N1, and then N2 you can find from the mole ratio. Just simply take them into comparison. Like the molar the N2 over N1 equals to 1.5 over 1, and then you have the value of N1 here, so you can next you can find the molar flow rate of the reflux one. So you just simply 1.5 times 75 equals to 112.5 kilomole per hour. That is the molar flow rate of the reflux one. Yeah.
Oh, okay.
And then you find the molar flow rate of the vapor feed to the condenser one here, vapor from top of the column. So you just simply make a balance lah, like input equals to output. So N0 equals to N1 plus N2. So you will get the value for the molar flow rate of the vapor feed here. So 75 plus 112.5 equals to 187.5 kilomole per hour. Yeah. And then since feed and product stream compositions are the same, therefore for the molar composition of the vapor feed one is equal to the here 0.961. So all the molar compositions are the same one, because the feed and product stream compositions are the same. You can verify it by calculating whether the input or the output are the same or not. Yeah. So is that clear?
Yep, I
Yes.
understand already.
Yes.
Okay.
Yes.
Okay, so let's proceed to the part C. The part C one. Okay, now it is supposed that a partial condenser is used, and then the reflux and the overhead product is in equilibrium at 40 degrees Celsius, and the overhead product flow rate and reflux to overhead product ratio having the values given in part B, which is 1.5 to 1, and then ask you to calculate the operating pressure of the condenser and the compositions of the reflux and vapor feed to the condenser. So do you guys understand the part C?
I confused a bit. I don't know how to do it.
Okay, I will explain it clear. Okay, now is the partial condenser is used. So if the partial condenser is used, the liquid condenser is returned as reflux. Okay, and for the overhead product one, it consists of the uncondensed vapor, which is none of the liquid is taken off as the overhead product one. So in this case, the reflux, which consists of the liquid, and the overhead product, which consists of the vapor, is in equilibrium at 40 degrees Celsius. And when they are in equilibrium at 40 degrees Celsius, let me show you. What is it? this one. When the the reflux, which consists of the liquid one, and the overhead product, which consists of the uncondensed vapor in equilibrium, you can use the formula as shown here by the Rayleigh law, which is the YAP. YA means the mole fraction of the species in the gas phase times the P1, which refers to the operating pressure of the condenser, partial condenser, and then E is equal to uh, the SA1, which is the mole fraction of the species in the liquid phase times the pure species one, the vapor pressure of pure species. So I use this formula. So this one 0.961 is the mole fraction of the butane in the in the gas phase one, vapor phase one, times P, which is the operating pressure of the condenser, equals to S2. S2 is the mole fraction of butane in the liquid one times the vapor pressure of pure butane, which has been calculated as just now as in part A, 2830.70. Okay, from this one, you first you find the butane one, the butane vapor and butane liquid one, as mentioned here as since the reflux is in equilibrium with the overhead product one. Okay, and we have the mixture of the butane and pentane. So we have to find one by one first. For the butane one, you try to find you try to use the formula, this one, as I mentioned here in the book one. In this book one, you find you try to build a equation first for the butane one, and then same goes through the pentane one, because this 0.961 is the mole fraction of butane in the vapor phase. So it means that the remaining 0.04, which is the mole fraction of the pentane in vapor phase one, is belong to the pentane one. So you have to build another equation for the pentane one. So for this one, 0.04 P, times P, which is operating pressure, and then I multiply it by 1 minus S2, which means that this is the mole fraction of the pentane in the liquid phase one, and then times the vapor pressure of the pure pentane. Yeah, so since there are two values needed to find, which is the operating pressure and the mole fraction of the butane in the liquid phase, so just substitute equation 1 into equation 2 to find the operating pressure first. Okay, you do it and you will get the value of the pressure 1. And when you get the value of pressure 1, you can find the value of the S2 next, which is the mole fraction of the butane in the liquid phase 1. And then after you have the value of for the operating pressure 1 and the value of the mole fraction of the butane in the liquid phase, and then you can carry out the butane balance. You can just simply use the input equals to output. So as mentioned here, in the block flow diagram one, the end node is refers to the refers to the value 187.5 kilomole per hour, which has been mentioned here, and then times the S01, which is the mole fraction of the vapor feed to the condenser, and then equals to the output, which you just simply multiply 775 by 0.96 plus 112.5 times the 0.8803, and you will get the value for the mole fraction of the vapor feed to the condenser one. So we have done to yeah. So we have calculated the operating pressure of the condenser and the compositions of the reflux one, and the which means that the we have find the mole fraction of the butane in liquid one, which refers to reflux. Okay, and then the vapor feed to the condenser. So are you guys clear with it? Clear with my explanation? Yeah. Yes, I understand
Yeah,
already.
I understand.
perfect.
Yes.
I never thought to do like that because I can't
Yes.
understand the question.
Um, so
I'm so
overall,
blur.
Question is quite hard to understand for
Yes,
me lah.
my English not so good.
it's okay lah. It's okay if you understand now. Okay.